Problems with NumPy broadcasting. When we work with 1D or 2D arrays in NumPy, there are many challenges which we face. When we multiply element wise a column vector with shape A or 1 and a row vector with 1 row and A columns, it results in a 2D matrix of this shape and not a vector, because NumPy explicitly broadcast both vectors to 2D matrices before multiplying element wise. The same broadcasting behavior occurs if second input is 1D array instead of a row vector. NumPy treats 1D arrays as row vectors and during operation, leading to same outcome. The only case where expected vector algebra behavior occurs is when both inputs are column vectors or row vectors or 1D arrays, as their shape broadcast consistently. We'll see numerous cases based on this. First of all, we'll say that we'll create a 1D NumPy array, 1D NumPy array from the list, and a 2D array with column vector, this. Now case 1, when we perform element wise multiplication using this, we'll see that when the dimension of both the vectors is array 1 and array 2 is 4 columns 1 row, and the resulting multiplication element wise is this, which has 4 columns, so it is consistent. But in case 2, performing element wise multiplication of column vector and 1D array, so 1D array multiplied by a column vector, it will treat as a 2D array and the resultant will be a 2D. Now when NumPy uses this operator at the rate to multiply two 1D arrays, it treats one of them as a row vector and other as column, resulting in a scalar value. As seen in this example, performing multiplication of two 1D arrays, we use this array 1 and array 2, both are 1D arrays, and the resultant is a scalar, so we should be careful to using this symbol. Now we started from element wise multiplication, now we go element wise addition. Both of the 1D arrays are added and a resultant of the same size and shape is what we get. Now another case 5, performing element wise addition of a column vector with 1D array. Column vector with a 1D array, it broadcasts this array as 2D and both of them as 2D, and then makes them with this dimension. So now the third case is swapping matrix multiplication with element wise. Now consider a scenario where you want to perform a matrix multiplication, however by mistake you use asterisk instead of at the rate. Despite the incorrect, you will get the correct code because of the Python broadcasting. The shapes matching might lead you think that you're doing right, but in reality matrix multiplication is required. We'll see this. Now we will create a 4x4 2D array with random values between 0 and 1. This is how we use. And now randomly generated array with 4x4. Now case 6. Now we multiply array 1, which is a 1D array, array 3, which is a 2D array, using multiplication asterisk. So the resultant is a row vector. because the 4 and 4 will cancel out of the shape and it will get the 4 as the dimension. Now case 7. Now substituting at the rate with asterisk matrix multiplication with element wise. Now array 1 is 1D array and array 3 is 2D array. Now it broadcasts it and making with a dimension. Now compare both of the usages. At the rate matrix multiplication gives us the shape, it reduces the shape, and asterisk the element wise multiplication, it broadcasts it. Now similar observation can be made by using PyTorch instead of NumPy for matrix multiplication. We create 1D array, we create a 2D array, and now case 8 matrix multiplication involving 1D. So tensor 1 is 1D and tensor 2 is 2D. So we multiplied both of them, we get a tensor of 4 comma 0 with dimensions as we can see here. But if we substitute at the rate with asterisk between the 1D and 2D arrays, it will result in a broadcasted element wise multiplication of this shape. So we have to be careful if by mistake we switch over at the rate and asterisk. I hope you understand this. Thank you.